All right, 37 from the textbook. This airplane lands with a speed of 50 meters per second. Now look, when the airplane touches ground, are the wheels spinning yet? So imagine the airplane coming in, the wheels are not turning yet. But once the airplane touches down, the wheels are going to have to catch up to the airplane, right? So here's the wheel right here. So the wheel hits the ground. I want you to visualize this. The wheel hits the ground. Here's the ground right here. And then what's going to happen to the wheel? A point on the wheel is going to start to what? It's going to start to rotate, right? Now what's providing the torque here? When the airplane touches the ground, what provides the torque that causes this airplane wheel to start spinning? Friction. Friction between the wheel and the ground. That provides the torque. The wheel's going to start to spin. So what I've done is I've summarized the steps we're going to follow. This will make the problem more clear. So first step, find the angular velocity of the wheel after the 0.48 seconds. So see right here? So the 0.48 seconds, that's how long it takes the wheel to go from not spinning to spinning at its maximum angular velocity. Okay, so when the wheel reaches its maximum angular velocity, it's going to be moving. So the center of mass of the wheel is going to be moving with a linear velocity of 50 meters per second, right? Because that's how fast the airplane's moving. Okay. How about a point on the perimeter of the wheel? How fast will a point on the perimeter be moving? 50 meters per second. Hold on, let me move this eye. Get this eye out of the way. Come on, eye, you're in my way. We'll scoot this guy. Get over here. There we go. Okay. So a point on the perimeter, once the wheel starts spinning, it's going to have a tangential velocity of 50 meters per second. Make sense? Now, how do we find the angular velocity of the wheel after the 0.48 seconds? Well, velocity, linear velocity for a point on the perimeter of the wheel is going to equal angular velocity times radius. So the angular velocity is going to be the linear velocity over the radius. So it's 50 meters per second. We have the radius of the wheel as 1.25 meters. So this gives us an angular velocity of 40 radians per second. So that's the angular velocity at the end of the 0.48 seconds. Okay, second step. Find the angular acceleration of the wheel during the 0.48 seconds. So how do we find the angular acceleration? Well, we can do a rotational kinematic. So we go angular velocity final equals angular velocity initial plus alpha t. Do you guys recognize that equation? It's just a VF equals V initial plus AT. It's just for rotational. All right, so what's the initial, when the airplane comes down, before the wheel starts spinning, what's the initial angular velocity? 0. So the angular acceleration is going to be the final angular velocity over time. So that's 40 radians per second in a time of 0.48 seconds. This gives an angular acceleration of 83.3 repeating radian per second squared. All right, so now we have the angular acceleration of the wheel. Now, next thing, we're going to do a free body diagram. Okay, so remember that number. I'm going to revert this back. Oh, dude, I thought I saved it, sorry. Okay, so shrink this down again. Sorry, guys. Put that up there. Here's the wheel. Okay, we're going to do a free body diagram for this wheel. What are the forces acting on the wheel? Well, we have mg down, which they tell us is what, right here? Each wheel supports a weight of 14,000 newtons. So what's the down force on the wheel? 14,000 newtons. That's the weight it's supporting. So what's the upward normal force? The wheel is on a surface, so what's the upward normal force? It's got to be 14,000. Well, in fact, let's just leave it like that. We know it's 14,000 because there's no vertical acceleration. Now, there's one more force on the wheel. Down here, so here's the ground right here. When the wheel hits the ground, we said that friction is what makes it start spinning. Which way is friction going to be on the wheel? To the left or to the right? to the left. Friction is going to be this way. And guys, friction is still coefficient times normal force, like that. Okay, so there's our free body diagram. So now we're going to sum the forces in the y, just in the y. So in the y direction, we have normal force minus 14,000. Sum of the forces equals ma. What's the vertical acceleration? 0. So the normal force is equal to 14,000. We're going to use that in a second. Okay, so now we sum the torques. What's the only torque on the wheel? Friction. So friction is mu Fn times what? What's the lever arm to that force? The radius, which is going to equal I alpha. Guys, we know, look at this equation. Look at this. Look at this. We know everything in this equation except what? Mu. Mu is going to be equal to I alpha over FNR. So now you plug in. The I was right here. So I'm going to do it up here. I'm going to plug in up here. So I is 110 kilogram meter squared. Alpha, we found out, was 83.3 radians per second squared. And then normal force is 14,000. And then the radius is 1.25 meters. 0.524, the coefficient.